Welcome back to the course. We were looking at 2D heteronuclear NMR spectroscopy in the last class. We started with looking at HSQC, which is a very basic 2D NMR experiment, and it can correlate either proton with carbon or proton with nitrogen. So, we looked at the pulse sequence a brief. Now, let us continue to look at that. A variant of HSQC is HMQC, which we will see next. So, we saw in this HSQC you have basically 3 building blocks or 3 important parts. Number 1 is this called inept. Inept is the part of the sequence where the magnetization is transferred or the polarization is transferred from hydrogen or proton to carbon. It can be also nitrogen, it can be phosphorus, it can be fluorine, it can be any heteronucleus, but in biomolecules we will mainly focus on carbon and nitrogen. So, we will see that this inept is basically the important part. It does the work of polarization transfer, which we saw in the previous class. Why is it very important? So, this is the first part of the sequence. Once you transfer the polarization to carbon from proton, the carbon is now excited and the carbon chemical shift evolves during this period. So, this is this evolution which is shown here as cosine omega c into T1. So, you can see this period here T1 is shown and it is divided into 2 parts, half this side, half on that side, and in the center there is a 180 degree pulse on proton. And what is the function of this 180 degree pulse? The 180 degree pulse here is there so that the proton is decoupled from carbon. So, this is similar to this kind of decoupling which we have seen in 1D NMR or in carbon NMR, that we decouple carbon or proton during detection, but here there is no detection, that this is called an indirect evolution period. So, therefore, in this particular period we do not apply a continuous decoupling as shown here, we apply simply a 180 degree pulse, and this 180 degree pulse has to be applied at the center of the evolution. It should be exactly at the center, it should not be displaced on this side or that side, and then the decoupling will not be complete. So, this is a second important part in this pulse program, that is the evolution of carbon chemical shift during T1. Then after this period is over, you apply another 90 degree pulse. So, the carbon magnetization which was along the x or y plane is taken to z axis by this pulse, and the proton which was along z axis because of this pulse now comes back to x or y plane. So, you see this is exactly the reverse of this. So, this is the reverse of this particular step. So, we use the word reverse inept, but otherwise both are inept, they are actually polarization transfer sequences, they are transferring magnetization from one spin to another spin, but the way the function of this is to come from proton to carbon, here it is back to proton. So, now during this period again there is a evolution due to chemical shift and coupling, but chemical shift is suppressed because I mentioned in the last class that if we have a something like this is called a spin echo sequence. Here you have a delay or a tau period, some delay which can be any duration, 180 degree pulse, okay, and then another delay. So, if there is a sequence element like this, it suppresses chemical shift evolution. So, this is for that nucleus where the 180 is applied. So, in this case the 180 is applied on both proton and carbon. So, there is no question of chemical shift on proton and carbon, but the coupling is not suppressed because of this. The coupling continues to happen, and that happens during this total period, that is 2 times tau. So, 2 times tau is 1 by 2 j, and we did some calculation and showed that you have to adjust this tau value so to the j value. So, this j is in the denominator, remember, like here it is not in the numerator as it appears here. So, 1 by 4 j in the denominator, 2 times is 1 by 2 j, and that turns out to be about 1.8 in plus 1.8, the total is about 3.6 milliseconds from here to here, assuming a coupling value of 140 hertz. So, remember we are tuning it to a 1 bond coupling. So, 1 bond is shown here, this example. So, therefore, the transfer will take place only from this proton to this carbon, no other carbon or no other proton. So, that is important to keep in mind because this is very specific to a directly attached carbon. So, this experiment now at the end of this here we start detecting the whatever is magnetization is present on proton, and what is that present on proton? The one which we started from here is the same magnetization which has gone to carbon, come back to proton, is available now for detection, and that is detected as cosine omega h T2, because this is during T2, and during that period we decouple proton from carbon because J coupling is present. So, this should not split into 2 because of J coupling. So, now we can see here mathematically what has happened is we have correlated the carbon chemical shift evolution which happened during this period with the proton chemical shift evolution during T2. So, therefore, it is a 2D correlation information, 2 dimensional information, because every carbon is connected now to its directly attached partner proton. Okay. So, that is the important point here in this experiment. Now, coming to about delay values, which already we discussed last time, a bit more I can tell you today is that this value of J varies a lot in proton to carbon. So, this is roughly for methyl protons is of the order of 125 hertz, and when you go to the aromatic spin system which is often the case in protein, we have 3 or 4 amino acids which are aromatic in nature, they will have a coupling of this. So, you cannot satisfy one delay period for all the carbons or all the carbon proton pairs. So, if you satisfy this delay or adjust this delay to 125 hertz, then this will be way off. So, this is called mistuning of the inept delays, but that is bound to happen because we can't have a single number. So, one of the areas of research in NMR has been to have what is called as a broadband inept, meaning given a single delay value, can I still get optimal transfer between proton and carbon all the way for methyls as well as aromatics with a single delay, value, and that there are several papers published on that. But typically what we do is we record 2 different HSQCs. One HSQC we record for the aliphatic part, that is for methyl, methylene and methine part, and one HSQC we record separately for the aromatic part in proteins. So, we have aromatic HSQC which detects only the aromatic portion of the molecule and aromatic amino acids such as phenylalanine, tyrosine, tryptophan, histidine, etc., and one experiment only for the other part of the protein, that is aliphatic, the hydrophobic amino acids or the non-polar amino acids. So, this delay period is something which we already discussed. So, this varies now like this depending on the J values. So, if I use a very short day, suppose I use 220 hertz here, and you can calculate 1 by 220 times 4 is almost close to 1.1 milliseconds, that is for 1 tau value. So, you know, if I multiply with 2 times, I will get about 2.2, 2.5. So, that is the typical value delay period we can use if we are studying the larger coupling. If you have a system, if your molecule has larger coupling value, and for smaller couplings like methyl, we go to higher delay periods. So, this is a very important part in HSQC to understand what are the different components in this pulse program, what are of these things doing. Okay. So, let us continue now and look at the peak pattern. How does the peak pattern of this comes in this spectrum? So, what kind of peaks you expect to see? So, here is an example of a simple amino acid glutamine, this is one amino acid. So, you can see now what are the correlations we can expect to observe in this spectrum. So, the first peak which is here is downfield, meaning it is close to 60 because of the de-shielding from these groups. So, because of that this is de-shielded, and this proton or this carbon proton pair, remember this is we are all detecting these pairs here, carbon on this axis and proton on this axis. So, this pair comes around at 60 ppm. Now, the next pair which we will detect is methylene. Now, you can expect, you may think that these two are equivalent, but actually they are not, because there is a chiral carbon here. So, there is asymmetry in this molecule, the molecule is not symmetrical as we discussed for chemical equivalence earlier. So, therefore, in principle these are not chemically equivalent, they are called distereotopic or prochiral protons. So, their chemical shifts are proton chemical shifts will be different, which is not shown here, but if you record a spectrum with very good resolution, it will come as 2 peaks here. Now, in sometimes they can be well separated, so they will come far apart. So, when we look at a real carbon proton spectrum of a protein down the line, you will notice this difference. So, now here you can see this proton, there are 2 protons now, but the carbon is attached the same, they are attached to the same carbon. So, that means there will not be any shift difference in the carbon. Carbon is only single carbon, which will becomes around 30, but the protons will have 2 different values if they have. In this case, I have not shown it like that. Now, the next one is the remaining carbon proton pair, which will come slightly down now. And why is it again down compared to this green color here? Because of this amide group to which it is attached. So, there is a de-shielding effect because of that, and therefore, it comes downfield or lower or higher in chemical shift compared to the other proton. So, this is example of a simple glutamine spectrum. Now, you can see there is no other carbon proton pair in this left in this system. Carbonyl does not have a proton attached to it, and so on and so forth. So, only 3 peaks are expected in HSQC spectrum for this molecule. So, like this we can call it as a family of protons and carbons in a amino acid. So, we use the word spin system. So, we can think of this molecule or the whole molecule as one family, and in the whole molecule the spin system, carbon proton spin system consists of these 3 groups, methyl, 2 methyls and alpha, beta, gamma. Okay. So, this is the way how we have to think about spin systems in amino acids and proteins, because that will be very useful concept when we go for further assignment of proteins and structure determination. So, let us look at some more examples. This is isoleucine, and you can see in isoleucine again we have different carbon proton pairs, and let us see what are the ones which we see. So, the methyl group, this is called the delta, because you can start from here alpha, beta, gamma, delta. So, the delta proton and carbon of isoleucine are most upfield shifted, and why is this so? Because they are very hydrophobic and shielded from all the other functional groups. So, they are the most upfield shifted. Then you have this other methyl also here. So, this is called the gamma 2 of isoleucine. So, this is gamma 1, the one which is shown here is gamma 1 carbon proton, and this is gamma 2. So, for gamma 2 you will get again close to the other delta proton, delta carbon. So, these 2 come here. The next is the gamma 1 carbon proton pair. So, here you can see now there are 2 peaks, and this is because these 2 protons are not equivalent chemically, because as I mentioned in amino acids we have a chiral center, and also they are called distereotopic or prochiral protons, and they are not actually equivalent. They may have accidentally the same chemical shift value, but they will not be equal because they are having a different chemical environment around them, and there is no plane of symmetry which can be drawn to show they are equivalent. Then comes the beta proton, there is a single proton, single peak, and this comes around 39 ppm, and the carbon is 39 and the proton is around 2 ppm. And the alpha proton again is shifted down because around 60 ppm, mainly because of these 2 groups which are de-shielding effect, which have de-shielding effect. So, in proteins, one thing which I should mention at this stage, although we will again repeat this later on, is the C beta. The chemical shifts of C beta are very significant, they are signatures of amino acids. If I go back in this slide, if you look at this here, this is C beta here, and this C beta was somewhere around 29 or 30 ppm. So, that is a signature value for glutamine. So, one can actually try to identify glutamine based on this chemical shift. Of course, it is not that it is unique for glutamine, some other amino acids can also have the same nearby chemical shifts, but in general C beta chemical shift of amino acid helps in identifying that amino acid. Okay, it is like a unique identification for that particular amino acid. Similarly, for isoleucine it is always comes around 38 to 40 ppm independent of the structure. There is small variations will be there based on the structure of the protein, but normally it does not vary much. So, again it helps to identify an amino acid based on its C beta chemical shift. So, we will use this idea later on to see how proteins are assigned in chemical shift. So, this will be very useful. So, this is another example of another amino acid called threonine. So, in threonine this is a very interesting amino acid because at C beta there is a OH group. So, it will be nice to see what is the effect of this on the carbon and proton chemical shift. So, if you look at this now, again starting from methyl, as always methyls are upfield meaning they come around 10 to 30 ppm, and this is something which we have seen. The range of carbon chemical shifts was covered in the part 1D, where we looked at the range of the dispersion of carbon shifts. So, that is we saw that methyls always come between 10 to 30 ppm. So, you can see that is what is shown here. Now, if you look at the beta proton and carbon here, you can see that there is a very downfield shift, it is coming around 70 ppm. And why is that? That is because of this OH. The OH has a de-shielding electron withdrawing effect on both the carbon and proton. So, the proton is also coming around 4.5. So, you can see if you recollect the previous slides, we had the beta protons were not so downfield, they were coming around 2 ppm or 2.1, 2.5, but here it is coming around 4 to 4.5. So, that is why, as I said, that is why I said that amino acids C beta are very interesting or very peculiar, and for many of them they can be very easily used to identify what amino acid we are looking at. And this C alpha, it comes around again downfield shifted around 60 ppm. This is because now it has also it has also this effect and this effect, and also it has effect from OH. So, you can see there are 3 different, although this is OH is not really close to it, even then there is a de-shielding effect happening for this more compared to other amino acids. So, this is threonine's alpha is also coming down compared to other amino acids. Other amino acids we saw comes around 60, whereas this one comes a little bit down around 65. So, this is examples of different amino acids that we are looking at, because in this course we are mainly interested in biomolecular NMR. So, we are looking at all the amino acids as much as possible, not all of them, but representative example. So, example, now we come to the aromatic amino acid. Now, aromatic amino acid is a very interesting structure. So, you can see for all aromatic typically in proteins you will have this alpha carbon, this is amino acid. So, you have amino group, acid group. Of course, in proteins you will have a peptide bond. So, it will not be COOH or NH2, it will be attached to another neighboring amino acid this side and a neighboring amino acid this side. And you have now the beta, there are CH2 group, and which is case for all the aromatic amino acids. Then you have this rotation. So, what is shown here is this aromatic part, and what this red arrow indicates is that there is this aromatic along with OH, they flip in the horizontal axis on this axis very fast. So, this is called ring flipping, and which happens very high speed at room temperature. So, this aromatic ring is not actually sitting static, it is rotating very fast like the methyl groups around this bond. Okay. So, there have been again a research area on how can we slow down this motion of this aromatic ring flipping, and several papers have been published on at how to go down in temperature. So, one problem is if you go down in temperature, even at 0 the flipping is still very high. So, I have to go below 0, but if I go below 0 the molecules will freeze, I mean the sample will freeze, because these are typically made in water. So, how do I prevent freezing and still go to low temperature is the art which has been published. So, that is something we will not go into details now, it was just a digression to show you that yes, this ring flipping is actually a very interesting field research on its own. So, in a tyrosine now let us look at the chemical shifts. The CH comes around 60 ppm, which is as same as all other amino acids, because this has nothing special, it is similar to other amino acids. The CH2 comes around 40 ppm, 30 to 35, 36 actually, between 36 and 40, and again you can see there are 2 peaks here, and that is because these 2 protons are not equivalent. They are not equivalent, but they are attached to the same carbon. So, the carbon is the same chemical shift, but the protons are different, slightly different. It's about this is about 0.2 to 0.3 chemical shift difference ppm. Then comes the aromatic system. Now, if you look at the aromatic, we can think of some symmetry here. See, these two, as I said, they flip around the axis. So, they actually average out, which means these two protons are almost equivalent. They are not, they are exactly equivalent because they are flipping so fast, they see the chemical environment similar to each other. Similarly, these two protons will have a flipping around, because of the flipping they will be equivalent in chemical shift. And because of this effect, you will see in the aromatic part, which is shown here, which comes around 120 to 140. Aromatic, remember, always come this the range 110, 120 to 140 to 145. So, this is the range of chemical shift for carbon where aromatic comes. In terms of proton, they come between 7 to 7.5. So, this is something which many of you in chemistry are aware of. So, that is aromatic part, but as I said, because of the equivalence due to the ring flipping, not because of a symmetry in this system, because of the ring flipping, they are equivalent, and therefore, you see only two peaks, that is one peak from here and one peak from here. So, now you can think of which is which. The one which is upfield is this peak and one which is downfield is the other one. Why is it downfield? Because of the OH. So, OH group essentially causes de-shielding effect and it results in a downfield shift, similar to what we saw in the case of threonine and also glutamine. So, now this was example of HSQC we saw with some important amino acid examples. Let us come to the next experiment, which is very similar in terms of the information, or same in terms of the information provided by HSQC, but it is much simpler and more sensitive in nature compared to HSQC. So, it depends on what system you are looking at to study. Typically, HSQC is very popularly used because there are more versions in HSQC. You can have sensitivity enhancement and so on, but the problem with HSQC is the speed, and the speed here can be enhanced in HMQC by varieties of methods, which is again an area of research. So, there have been always equal usages. HMQC is also used and HSQC is also used. So, let us see how HMQC works, and we can appreciate the differences between the two as we go along. So, again in any pulse program, again there are three parts here to this experiment. One is this part here, okay, and the second is this is the inept part, and there is a inept again here back. Although you do not see that 180 degrees here like we saw in the HSQC, but we still use the same idea of polarization transfer like we do in HSQC. So, the polarization is happening because of J coupling. So, that is one thing you have to keep in mind. In heteronuclear NMR, any polarization transfer between two nucleus happens using the inept concept, inept block. Now, inept can be implemented by adding a 180 here to suppress the chemical shift, but to keep the coupling active. Here that chemical shift evolution happens, but there is again suppression which is taken care by 180 here. So, we do not have to bother about 180 here. So, this block actually does the same job from here to here as what we saw in the case of HSQC. And the third important portion of this experiment is this here, which is similar to what you saw in HSQC. So, if you recollect the HSQC part, this part is the same, there is no difference. And finally, you have detection and decoupling. So, let us go through this again step by step. So, you excite the carbon proton, first you excite the proton chemical shift. So, again remember we are in HMQC as well as same as HSQC. We look at only the directly bond proton to carbon pair. We correlate the proton chemical shift to its partner directly attached carbon chemical shift. We are not looking at proton to another carbon here, or neither we are looking for proton to another proton. So, there is only proton carbon correlation, and that too specifically only one bond similar to HSQC. So, this therefore, the coupling, the J value has to depend on this coupling value. Now, as we discussed, it has a range of 125 to 220 hertz, and therefore, you have to tune according to this chemical values here. So, now once you have this delay here from 1 by 2 j up to this much, the magnetization from proton which was excited here by this pulse gets transferred to this carbon here, but the carbon is not excited yet. So, it has to be excited by applying this 90-degree pulse on carbon. Once that happens, the carbon chemical shift evolves during this period, and that is what is similar to HSQC. We have a T1 evolution and there is a 180 right at the center, and that 180 is because we want to decouple the proton from carbon. So, then during that period here the carbon chemical shift evolves by according to this, and that is cosine omega c into T1. Once the evolution period is over, we have to transfer it back to proton for detection. So, that is called inverse detection. So, now proton transfer back to proton takes place through again a inept element, which is say called as reverse inept. Now, that during that period carbon now has gone from carbon to polarization has gone from carbon to proton, and proton now is evolved during T2 and detected during T2, and decoupling on carbon is carried out during that period to avoid any J interaction or to suppress the J coupling, and do that period you are evolving. So, you can see this part and this part is similar to HSQC, there is no difference as far as the evolution is concerned. But the major difference here is you do not have 180, 2 180s here and 2 180s here. So, the 4 180s which you saw in HSQC were extra, which are not used here. And what is the advantage? The advantage is in NMR technically, which although we will not be able to go into detail in this course, this 180 has a very bad spin inversion effect. It is not a broadband inversion. A simple 180 if you take in a general 180, it does not have a broadband inversion and refocusing effect. So, therefore, you lose the magnetization because we want to invert because of the 180. The job of 180 is to invert or refocus a magnetization. That is typically not very efficient in NMR 180. So, if you remove 180s like this, it becomes more efficient because the transfer efficiency overall is improved or enhanced. But one problem here is because there is no during this entire sequence, because the proton is along the xy plane. So, if you look at this here, we do not see any other 90 degree on proton, which means the proton is always in the xy plane, although it is refocused here, it is only 180. So, it is brings x to x minus x, y to minus y, but it does not bring x to z or y to z. So, therefore, this proton remains in the transverse plane, which means its relaxation is going on, T2 relaxation is going on throughout this sequence, whereas in a HSQC we bring it along z axis at this point and we bring it. So, from here to here in HSQC it remained along z axis. So, its relaxation was not affecting during the chemical shift evolution of carbon, but here it is now affecting, number 1. Number 2 is that the J coupling between proton to proton is active during this portion of the time, and this is I am talking about this proton to another proton nearby. Suppose there is another proton which is 3 bond away, that proton to proton coupling, or if there is a proton which is 2 bond away, a geminal proton, they will be coupled to each other and their coupling is sufficiently strong, and that coupling evolves or also takes place here, and mathematically you should add another term here which I have not shown. I have ignored that, but technically there is another term which is cosine pi j T1, means the J coupling also evolves, but that does not happen during the HSQC experiment, because in HSQC we put the magnetization of hydrogen proton along z axis at this point. This you should recollect from the previous slides. Now, when it is along z axis, the coupling will not evolve. So, there is a theorem or a theory in NMR which says if you take a magnetization along z axis, it does not evolve to with other protons due to J coupling. So, that because of that there is no J coupling between proton and proton, and similarly between proton and carbon anyway we had decoupling here and also in HSQC. So, that is not an issue. The main thing is proton to proton coupling is active here, which was not the case in HSQC. So, that creates an extra dampening or reduction in the signal because of extra coupling, which was not there in HSQC or suppressed. So, therefore, overall the HMQC reduces in sensitivity because of these factors. The one is the proton relaxation, second is the coupling which degrades the resolution also of the spectrum. So, it is therefore sometimes not popularly used for biomolecules. For small molecules it is very popular, but as I said, you can improve this sequence and make it faster with some latest technique development which has happened, and that therefore makes this popular if you want to record data very rapidly. So, this brings us to the end of the HSQC and HMQC. We will look at more detail of HMQC in terms of the quality of the peak pattern, again similar to what we saw in HSQC. But as I said, the HSQC peak pattern is same as HMQC, there is not much difference. So, as far as the peak structure is concerned, they all look same. So, in the next class we will look at some examples of HMQC, and then from there go on to another 2D experiment which is again very popularly used, and following that we will go into 3D NMR.